After. Tensor conductivity. Already.
Thank you. Alright, so I hope everybody can hear me. So let me what we had seen last time. So again, I'll remind you. So we are discussing the properties of Cartesian tensors. Or we started with what we mean by Cartesian tensors. And again, I want to emphasize all of this with respect to our three-dimensional space, Euclidean space.
Excuse me, ma'am.
Yes.
Ma'am, may you switch off the lights?
Okay, one second. Even the board light?
Yes, ma'am. Particularly on the boards.
Particularly on the boards. Is it okay now?
Yes, ma'am.
One more light. Is it fine? Is this all right?
No, ma'am. Previously it was okay.
One light.
Ma'am, yes, ma'am. Yes, ma'am. Now it's.
Because I think this will give you put light on the board. Is this okay?
Yes, ma'am.
Again, I want to remind you that please stop me anytime you during the lecture and ask me questions. If you find that something is not getting across, or if something is not being taught, you're not getting confused or not understanding it properly, or even after the lecture, you can ask questions. So please do that. Okay. So again, as I said, that what we did yesterday was that we defined what we mean by Cartesian tensors, and everything I did with respect to our three-dimensional space. And I've chosen this Cartesian basis. And we also did this with respect to what I called as rigid rotations. So this was a transformation which took you from a basis given by a particular choice of what axis. Again, I want to say we've chosen Cartesian axis, so E1, E2, E3. Okay, and again, I'm reminding you that I'm using these synonymously, I cap or J cap and K cap as unit vectors along the x-axis, y-axis, z-axis respectively, or E1, E2, E3 as basis vectors. So these are synonymous. And when we said that we want transformations which will take you from this, a linear transformation which takes you from this basis to another basis, in such a way that the inner product of two vectors in this space is preserved. And what we found is that such a transformation is an orthogonal transformation which satisfies this problem. And in particular, what this implies is then that determinant of R equal to plus minus 1. So transformations which take you from this kind of a basis to another basis in prime in such a way that the inner product of two vectors is preserved under the transformation is an orthogonal transformation. Linear transformation is orthogonal. That means the first line of the second column is satisfied. Our transpose R is R transpose and identity matrix, and which immediately implies that determinant of R must be either plus 1 or minus 1. Right. Then I said that yesterday I said that I'm going to now restrict myself to rigid rotations. So these kind of transformations. So firstly, this will preserve the origin. And when I say rigid rotation, it also means one more thing which I took it implicitly, but I did not state it explicitly. That it also means the following, that I'm preserving the sense of my coordinate axis. So here, for example, when we chose I, J, K like this, it's essentially I've chosen a right-handed coordinate system. Because I cross J will become K, J cross K will become I, and so on. And when I say I'm going to consider rigid rotations, it's not just that the origin which is being preserved or zero vector is being preserved. It also means I'm taking here I'm saying. So I'm also taking determinant of R equal to plus 1. Or in other words, if I started with the right-handed coordinate axis system, then I don't change the right-handedness or the handedness. I don't go to the left-handed system. I keep it in the same way. Or in other words, what this means is that I don't allow for reflection or number of reflections. So I don't ask for transformations like x going to minus x, y going to y, z going to z. So I'm restricting myself to those transformations which satisfy the condition determinant of r equal to plus 1. And later, when we see that these are what are known as proper rotations. So later on afterwards, we'll also discuss what kind of transformations do we need when we have determinant of r equal to minus 1. I will come back. So implicitly, I assume this. Okay. Then we defined yesterday. Okay. Given this, okay, I have defined yesterday that. So I'm considering now only what we mean by a tensor of rank n. So I define this in the following way, that is a quantity which consists of 3 to the power of n components. So there are 3 to the power of n components. So we are in 3 dimensional space, remember. And I'm going to label this object by n subscripts, I1, I2, I3, and so on up by n. And so I have this quantity which consists of 3 to the power of n components. And if the transformation properties of this set of 3 to the power of n components, so this I say with respect to the basis p, and with respect to the basis p prime, if the transformation follows this law, then, so if these 3 to the power of n components transform among themselves according to this relation, then we will say that it's a Cartesian tensor of rank. Or we will say that these 3 to the power of n components forms a Cartesian tensor of rank. And this n can take 0, 1, 2, 3. So I can get a tensor of rank 0, which essentially means that there is no subscript here. So it's just one quantity, because 3 to the power of n will be simply 3 to the power of 0, so it's only one quantity. And I have nothing here. So which means that in that case, I'm simply going to get S prime equal to S. And that is something which we call as a scalar, which we know as normally as a scalar. So a tensor of rank 0 will correspond to our usual scalars. A tensor of rank 1 will have 3 components, and then in that case, I will have just one index here. So I will simply get, which I will write like this, Bi prime will be equal to then Ri j V. And this simply defines for us then a tensor of rank 1, or what we will usually call as a vector, a 3-dimensional vector. A tensor of rank 2 will have 2 indices because m will be equal to 2. M goes up to 2. So then I will get C prime ij will be equal to, according to this definition, Ri k R J N T. Notice that I'm using now summation in convention. So this K here and L here are repeated indices, so they are summed over. And the 3 indices are ing. So this will correspond to the transformation properties of a second rank tensor. And the second rank tensor will have 3 into 3, so 9 elements of them. So the 9 elements will get mixed up in the rotation, under rotations in this possible or in this particular case. Only then I will call that as those 9 elements constitute the second rank tensor. If I have a third rank tensor, then in that case, of course, I must get one more here. So let's call this as ij MC. So I will get here this. So there will be 27 elements now, and I will get 3 R's. But also please notice how these summation indices are there. It's not just matrix multiplication. And now it will become EK. So now the dimensions for the summed over indices are K, L, N, and the 3 indices are IJ, and it goes up. So this is the way we define for ourselves tensors. And yesterday I demonstrated for you also with an example that examples of tensors, and in particular we took vectors at that point. So we saw that if I have the usual position vector x1, x2, x3, these are the three components along the x-axis. If I have the usual position vector, some point P, then R has these three components x1, x2, x3, x, y, z components. So this is your R. Then you know that R will go to R prime. Or if I look at the component form, you can very easily see that xi prime will be equal to rij. So in the new basis, the components are given by that relation. And again here I takes values 1, 2. So therefore your position vector, that's why you call it a vector, it transforms as the three components of a tensor of rank. On the other hand, I showed you yesterday that if I take this x2, x1, x3, this set of three quantities, if I define this set of three quantities, and if I, so I demonstrated this explicitly by considering a particular R matrix or a particular rotation matrix, and we saw that this does not constitute the components of a vector. And did anybody check out this particular exercise which I gave you? X2 minus x1, x3. I asked you to find out or verify that this transforms like a vector. Did anybody do it? Yes, no? Maybe. Partially. I'm giving all options. You know, sound travels at the speed of what is the speed of sound? The way it is being transmitted is through electromagnetic signals, right? So it should take, yes?
Ma'am, we decided to do it after exams.
Okay. So explain that, please. That's fine. Okay, fine. So I'll ask you the question after the exam. All right, that's okay. So anyway, the point I was trying to make was that it's not that any arbitrary set of three quantities constitute the elements of a vector. And similarly, what you will see later on, I'll give you examples later on, that it's not that any arbitrary, for example, 9 elements will constitute the components of a second rank tensor. Only specific values or specific quantities will constitute the components of a tensor. So this definition is quite restrictive. All right. Next one. Yes.
Ma'am, I have one question.
Yes.
When we are dealing with Cartesian tensors in Cartesian coordinate vector space, this is my real space.
Yeah.
So, my rank 1 tensor, Cartesian tensors represent vectors here,
Yes.
means physical
Yes.
vectors.
Yeah.
But what does higher order Cartesian tensors physically represent? Do they have any representation?
Yes. Yes. Second rank tensor, for example, you can think of as a matrix. So first rank tensor is like a column vector. You have x1, x2, x3 vectors. Okay. Second rank tensor will become like a matrix. All right. And from physics point of view, if you look at it, I'm not writing comments. So I get. Okay, so I get T11, T12, T13, so on. Let me just write it in a minute. T23. So I can arrange it at least in the form of a matrix, of a 3 by 3 matrix with 9 elements, and with the 9 elements transforming under rotations in this specific form. This is the first rank tensor. All right. Now you can ask me that what physical application is there for a second rank tensor. So right now I will just tell you, this is one thing which you all encountered actually. But I'll come back to this example a little later. All of you have encountered this moment of inertia tensor. That means if I have a rigid body and then if I figure out what is the inertia, moment of inertia of that rigid body. So if you look at it, and if it's not isotropic, then you will find that the components of that object actually form the components of the second right tensor from a physics point of view. And then I will discuss practical physics examples a little later once I finish a little bit more of the properties of tensors. Okay. Another one which is the electrical conductivity. So you have the Ohm's law. Anyway, as I said, I'm going to discuss this a little later in, with specific examples. But this is something which all of you actually have encountered. And perhaps you have also encountered quadrupole moment in electrodynamics. That also actually the components of the quadrupole moment also can be written in the form of the second right tensor. And I don't know if you have this, maybe you have not encountered, but perhaps also possible that you have. So if you have an elastic body, then I can push it, I can pull it. So then the push and the pull can put into how much push is there and how much pull is there. So that gives you also a twisting. So this can be put into the form of a tensor, which is usually called as a stress strain tensor. And these are, there are actually very valid reasons for studying about tensors, both from point of view of classical physics. Classical, when I say classical, non-relativistic physics, for example, this is really non-relativistic, okay? As well as later on you will see that there's a lot of practical applications in astrophysics and quantum mechanics and so on. And I will discuss examples quite extensively. Okay. So yesterday then what we saw, what I showed you also is that given two vectors, I mean, if you go back to what we already know, that if I have two vectors u, v belonging to a vector space, then we know that u plus v also belongs to a vector space. Or in other words, it's also a vector. Or in other words, I could discuss an operation of addition of vectors. And we could do that here also. Because now if I have two vectors, I know that suppose u is a vector and v is a vector. So u will be represented by these three components, u1, u2, u3. V will be represented by these three components, v1, v2, v3. And again, all of this is with respect to a particular basis. So I can also find out what is u plus v. Now these are simply as this is now represented by u1 plus v1, u2 plus v2, and u3 plus v. I can ask now the question that this quantity u plus v, which is defined like this, does this transform like a vector? Or in other words, does it transform like a rank 1 tensor? Given that u and v transform like a vector, or in other words, u and v transform like a rank 1 tensor. And it's easy to see that if u and v transform like a rank 1 tensor, then u plus v will also transform like a rank 1 tensor. So all you have to do is to demonstrate that u plus v is also a tensor of rank 1. All you try to find out is what are the components of this in the new basis. Okay. Or in other words, just find out what is ui prime plus vi prime. So if I call this as w, so if I say w equal to u plus v, which is given by this, so that means wi equal to ui plus vi. I equal to 1 is 2. So then I can see that wi prime. So all I have to check is whether the transformation properties satisfy the definition or not. Now wi prime by definition is going to be ui prime plus vi prime. That's how we have defined my object. And this, because u and v themselves are tensors of rank 1, ui prime will be related to uj by this formula, uj. Again, here I am using summation convention. Plus, vi prime I know again is defined as rij vj. Notice that because I have I here, I am using both I here. And because these are two different expressions, I can use ij. J is a dummy index, but still I am having a summation here. So I can use the same j here, both ways. Okay. And then I can write this now as rij uj plus vj. Where this plus is our usual algebraic addition. And what is this? This is nothing but Rij W. Therefore, is that Wi prime is equal to Rij W. Or in other words, what we can see is that if I define the algebraic addition of the vectors in this fashion, then W equal to U plus V transforms exactly like the tensor of rank 1 if U and V themselves transform like tensors of rank 1. Or in other words, I can define addition of tensors of rank 1 and I get back again tensor of rank 1. Similarly, I could also do a subtraction. So I could also consider U minus V. Again, this is our simple algebraic subtraction. So I can define it like this. This becomes now this. So this will become this minus sign here now. And I'll get minus here and again this. So I can now define, if I define U minus V in this fashion, then again I find that W will transform like the components of the tensor of rank. Or in other words, I can define addition and subtraction of vectors or tensors of rank 1, I get back again tensor of rank 1. Now you can ask the question, can I generalize this to higher tensors or higher rank tensors? What we'll say is we can do this. So now let's assume that I have a rank M tensor. So what I can do is I can add these two tensors of the same rank. So let's say that I have a tensor of rank M. So suppose I1, I2, A is a tensor which has rank M. So I have M subscripts to label that tensor. And let us say that I have another tensor which is also a tensor of rank M. Now I can define the algebraic addition. So I'm basically taking the I1, I2, IMF component and adding of A and adding that to the I1, I2, I2, IMF component of B. And let me call this as Si1, I2, I2. So this has 3 to the power of n components. This also has 3 to the power of n components, and I'm adding those n components in this specific way. Here, this is simply our usual algebraic addition because each of these components is a real number. So again, this object has 3 to the power of n components. So again, I can ask now the question that this particular object, does this transform like a tensor or not? Okay, and it's easy to check that. So you find out what is Si1, I2. So again, see whether the transformation properties are satisfied. So by definition now, S prime, I1, I2, Im should be equal to A prime, because if this is a definition in one basis, it's the same definition should hold in any other basis. So Im plus B prime. Okay, this is by definition. But we know because that A is a tensor of rank M, we know how this transforms. Again, B is a tensor of rank M, so we know what is the relation between B prime and B. So I use that. So the relation will give me I1, I2, Im. Sorry. So for this, I can write it as Ri1, I1, J1, Ri2, J2, so on, Rim, Jm, A, J1, J2, J. So A prime I1, I2, Im is related to A, J1, J2, Jm with this fashion because it's transforming like a tensor of rank M. Similarly, I could write for this also. So this again will become Ri1, I2, so I1, J1, I2, J2, Im, Jm, V, J1, J2. And once again, by using the same logic which we did earlier, that if these are just real number addition, simply algebraic addition. And so I can combine these two relations and write this as. So this tells me then that S prime I1, I2, Im equal to Ri1, J1, I2, J2 plus But what is this? This is nothing but your S, J1, J2, Jn by definition. So this gives me S, J1, J2, Jn. And I have here R, I1, J1, J2. Or in other words, your S prime, I1, I2, In is related to or transforms as Ri1, J1, I2, J2, Rin, Gn times S, J1, J2. Or if I define this object like this, it tells me that this quantity transforms like a tensor again as a tensor of rank. So therefore, what I can do is I can add two tensors of the same order, and what I will get is another tensor of the same order. And similarly, I could also do difference, means I can subtract. So one can also define addition of tensors of the same rank, and one can define subtraction of tensors of the same rank. You verify for yourself, this also will transform like a tensor of rank. So if I have two tensors of the same rank, I can add them, I can subtract them, again I will get back a tensor. But note that it will not make any sense for me to add or subtract tensors of different rank. That means it won't make sense at all for me to add, say, a vector and a second rank tensor. Because a vector will have 3 components, a tensor will have, second rank tensor will have 9 components. So I can't, if you remember the way I went from here to here, it's because both of them had exactly the same components and the coefficient was exactly of the same number of r's were there. That's why I could put them together. So I can only add tensors of the same rank, or I can subtract tensors of the same rank. I can't do that. I can't do such an addition or subtraction operation with tensors of different rank. So what we learned from this therefore is that I can do addition, subtraction of tensors of the same rank, and I will get back tensors of the same rank. What else can I do with this? Now notice one thing. Let me just. So consider now, suppose I have a kth rank tensor. Let's say I have a tensor of rank tensor. Okay, let it be a tensor of rank. I want to maybe I just want to also say. So let T be a tensor. So sometimes I will just use T without specifying the components for defining a tensor, just like we use U without specifying U1, U2, U3 for describing a vector. So I will use this notation T for describing a tensor. So let T be a tensor of rank T or rank tensor. What this means is that I have 3 to the power of n components which can be labeled by this I. Before I go to this, maybe I'll do it first. Second, let's do it with second rank. Then I will. So let's say. So this means I just have Tij. Okay. Now let me say that I label the tensor like this. So the same T is there. So whether I have Ij or Ji, if this transforms like a tensor, what about this quantity? Will it also transform like a tensor? It should make no difference, right? Because see, Ti, when I write Tij, I and J are like I is 1, 2, 3, J equal to 1, 2, 3. These are free indices. So whether I use I here or whether I use J here, it should make no difference here. Do you understand that? Because it is just an index, it's just a label. Is this clear? So it's like this. That's when I want to be. So I'm replacing the second rank tensor by a matrix. So I have T11. So this is like saying that T here and I is this row and J is the column index. So I have T11, T21, T31. T21, T12, T13, T22, T23, T31, T2, and T3. Now, whether I call the column row index as I and column index as j, or whether I call it as row index as j and the column index as I, it doesn't matter. All that I know is that j will run from 1 to 3, I will also run from 1 to 3. So, it really makes no difference. But where it will make a difference is when I take explicit elements. That means once I specify for you what is I and what is j. See, when I write it just like this, it means I can take all possible values, j can also take all possible values, and similarly for this. But if I specifically write for you, say T12, and then I write T21, then these are two different objects. Because T12 is this element, while T21 is this element, which are obviously in general quite different. It can be quite different. So that distinction I think you should keep in mind about when indices are in, or when we label the object by some indices. So often we are interested, for example, now I have written this explicitly the second rank tensor, let this be some second rank tensor which has 9 elements, and we often want to figure out, for example, if there's some, I mean, so not figure out actually, sometimes it may be that your T12 and T21 are not really different. Okay. Now if your Tij equal to Tji for all ij, or in other words, T12 is the same as this is the same as this is the same as this. For diagonal, it makes no difference because it's a T11. Then in that case, what kind of a matrix is this? Think of it first as a matrix. Suppose this element is the same as this element is the same as this element, and this element is the same as this. Then in that case, what would you call this matrix? Yes. So if this is true, then I will say that P is a tensor, a symmetric tensor of tensors. So the same tensor of so if the condition is right, then in that case I will say the symmetric tensor of that. Now, if instead of having plus sign here, if I had minus, what will you say? That means T12 is the same as minus T21, T13 is the same as minus T31. In that case, what will you say? So suppose I had this relation that Tij equal to minus Tj. Then what would you call such a matrix? Think of it first as a matrix. This equals
Skew symmetric.
Pardon?
Skew symmetric.
Symmetric or anti-symmetric. And further, what this immediately tells you is what can be T11 in this case?
0.
0. So what this tells you is that your matrix T must be of this form. 0, because all the diagonal elements must be 0, because if T11 is equal to minus T11, please remember we are talking real elements. So if T11 equal to minus T11, then it tells me that it must be 0. Similarly for this, for all. And then it tells me that this is T12 minus T12 here, T13 minus T13 here, T23 minus T. So this is something which I will call as an antisymmetric or a skew symmetric matrix. And we use the same definition here. That if your Tij equal to minus Tji, I'll just write it like this, it means the same thing, okay? Then T is an antisymmetric tensor. And in particular, what this tells me is that the diagonal elements for the tensor of, that means 1t, 1, 1t, 2, 2t, 3, 3 is equal to 0 identity. That's what this tells me. Right? Now I can generalize this to higher order tensors in the following way. Consider now, suppose I have an mth rank tensor. I have I1, I2, In. Okay, so let's write. Let me say I3 and I. Now, if this is true, if this equal to, I will write it. So if I1, I2, I3, so on up to In equal to T, I2, I1, I3, and so on up to In. So I've just exchanged the first two indices. Then we will say that T is symmetric under exchange of first two subscripts. So it's a tensor of under exchange of first two. So for higher order, so this is n greater than 3, or you can 2 also. For n equal to 2, you simply get symmetric. Or it is symmetric with respect to the first two subscripts. Okay. I can write exchange. Sometimes you will find in some books it will be simply written with respect to first two subscripts. So when we go to higher order tensors, when I want to talk of symmetry, and similarly I can also define for antisymmetric, but I have to also mention which two subscripts I am discussing. For a second rank tensor, it simply is, I can simply write it as symmetric or antisymmetric. But for higher order tensors, I can say that it is symmetric with respect to first two subscripts, antisymmetric with respect to first two subscripts. Sometimes it could be that I would have symmetry with respect to the second and the third, or maybe any other two indices. So the symmetry and antisymmetry for higher order tensors will also specify which subscripts we are talking about. And in general, of course, your tensors, even for example here, in general, any second rank tensor doesn't have symmetry or antisymmetry property, but I can use the following way. So I can make it right. I can write a general. Okay, now I write for a second rank. I'm again coming back to second rank tensor. So let's suppose T is some arbitrary second rank tensor. Then I can write this in the following way. So I add, because now I know that I can add tensors of the same rank, so I'll add it in this fashion. See, I have not done anything here. I have half Tij plus half Tij, that is going to give me simply Tij. And half Tji minus half Tji is 0. So basically, I just added and subtracted the 0. But let me call this combination now as, okay, so let's call this whole combination as Sij. Tij plus Tji, let me call it as Sij. And let's call this one as Dij. Because we have now defined what we mean by addition and subtraction of tensors. So here I'm adding and subtracting to second rank tensors. So this particular one I call it as Dij, and this particular combination I call it as Sij. Now, what kind of a tensor is Sij? What is okay? Suppose I have Sij. So I have defined Sij like this. So Sij and Sji, is there any particular relation? Okay, what will be Sji given that Sij equal to this? So Sij by definition is half times Tij plus Tji. Okay. See, that means S11 will be like simply T11. S12 will be half times T12 plus T21. S21 will be half times T12 plus T21 again. Okay, so that's how it goes. Now, if I have Sij like this, what is Sji by definition? I'm doing all this a little bit elaborately because so that I want you to learn how to manipulate indices and how to manipulate equations which contain these kind of subscripts and operations using this. By definition, what will be SGI? See, whenever I have the yes,
Half of TJI plus TIJ.
exactly. So you just use straightforwardly first subscript, then second subscript plus TIJ. But this is simply algebraic addition, so this is the same as your this one. Because these are nothing, there's no difference. So after I'm just adding same real numbers, so there is nothing but equal to SIJ. So your SJI is the same as SIJ. So in that case, what will you call SIJ? What kind of tensor is this?
Symmetric tensor.
See, first of all, you can see because I just added two tensors of the same rank. This is a tensor, and because it satisfies now SGI equal to SIJ, it is simply a symmetric tensor. So your SIJ is a symmetric tensor, symmetric second rank tensor. You see how we are starting with our definitions and then going to higher order tensor. Similarly, here now I have taken the difference of two tensors of the same rank. So therefore, again, I'm going to get a tensor. So this Dij is again a tensor of rank. Okay. So if I now write Dij to be equal to this, what is Dji? By definition, it will be simply this minus this. But what is this relation between this and this? So Dij equal to this. Now Dji, I've just taken the definition, the first subscript here, the second subscript here, then the first subscript here, second subscript here, and first subscript here. But what is the relation between Dji and Dij? From here.
Minus of Dij.
Minus of each other.
So what kind of a matrix is D? Or what kind of an object is D?
Antisymmetric tensor.
So what you find therefore is that this is an antisymmetric second rank tensor. So therefore what we find is that any arbitrary tensor, second rank tensor, can be written as a combination of a symmetric tensor and an antisymmetric tensor by using this. So I add Tij plus Tji, that will give you the symmetric part of it, and the antisymmetric part will come from Tij minus Tj, and they will be divided by 2 just so that it gives the same combination. And this is exactly what you did for matrices. Any arbitrary matrix can be written in terms of a symmetric matrix and an antisymmetric matrix. That is simply given. Right? And it's easy to say that I can do this generalization, or I can generalize this to any higher order tensor by just writing it in the following. So any higher order tensor, I can write it as, so I'm writing this like this, I1, I2, In. And if I'm only worried about the first two indices, I can write it as, so I can symmetrize and antisymmetrize with respect to say the first two indices in the following. I put one more index here, I think that's so. And again, if I call this as, so again here I've added two tensors of the same rank. So obviously this is again a tensor. Similarly, this is again a tensor. And I use the same label here. I call this as Si1, I2, I3, In. And I call this as Di1, I2. So what I find therefore is that I can write any tensor. So this I1, I2, I3, In can be written as equal to Si1, I2. where my Si1, I2, I3, Im equal to this, and Di1, I2, I3, Im equal to this. And what you can see is it's straightforward to see that your S tensor is a tensor of rank M, which is symmetric with respect to I1, I2 indices, the first two indices. While your D tensor, the tensor D, which is defined like this, it is antisymmetric with respect to the first two indices. Okay. So, or in other words, I can always write my tensor as symmetric, as a combination of two tensors, one of which is symmetric with respect to the first two indices. Here I have done with respect to the first two indices, symmetric with respect to the first indices, and here I have got the quantity which is symmetric with respect to the first two, antisymmetric with respect to the first two indices. Okay, again, you can ask why are we doing all this? You will find that there are a lot of practical applications when we want to write, or when we discuss later on physics examples, where it's useful to write tensors in this form using this symmetric properties under exchange of two indices. So I have given you the examples or illustrated for you with respect to the first two indices, but I will as well do this with respect to other indices. Depends on what you are interested in. Okay. So what we have learned therefore is that I can now add tensors of the same rank, I can subtract tensors of the same rank, and in this process I have also discussed or defined for you what we mean by symmetric tensor, which is symmetric with respect to first two indices, antisymmetric with respect to first two indices, and so on. But then you can also ask, can I do other things? Can I multiply two tensors? Is it possible for me to multiply? We have actually seen an example of this already. So yesterday when I showed you the example of this quantity, xi, xj. So I took the position vector and I said that construct this quantity, xi, xj. These xi's are the components of my position vector. So there are three components. Xj are again the components, these three vectors. And so we find from this I get 9 elements. And what we saw was that given that xi is transformed like the components of a vector or a tensor of rank 1, then this object or these 9 elements transform like the components of the 9 components of a second rank tensor. And I call this as the outer product of these two vectors. Outer product as opposed to the inner product. The inner product gives us a number where I'm getting the scale. So this in some sense is that I have multiplied in quotes tensor of rank 1 and another tensor of rank 1, and what I call is a tensor of rank 2. So therefore what I can do is I can generalize this now and say that I can construct outer products of tensors of two. So I just write it for you. An outer product I can construct of tensors. Okay, maybe I should just show you this one. Let me just one more thing. So I constructed two tensors. Let me again just demonstrate this. So I took this xi, xj, xj. This was tij. So by multiplying, again this is in quotes, by multiplying two tensors of rank 1, I got a tensor of rank 2. Now I could also do this. Suppose I construct this object, xi into tj. So this is a tensor of rank 2. This is a tensor of rank 1. And what you will find is that this quantity now will transform like a third rank tensor. Okay. So this is like taking the outer product of a tensor of rank 1 with a tensor of rank 2. And then getting a tensor which is of rank 2. So in general then what I can construct is the outer product of tensor of rank n with tensor of rank n, and what you will get, so if I take the outer product, it will produce, so it will produce for you a tensor of rank. What will be the tensor? Rank. So if I multiply in course, that tensor of rank m and n, outer product if I'm taking, what will be the resultant tensor rank?
3 raised to m plus n.
Huh? No, the rank of the tensor. not how many components. Components
M
is
plus N. M plus N.
Or in other words, the way you do it is just the following. So if I write it formally, so this particular tensor, so if I take a tensor say of A, suppose A is having rank M. So it will have M I N. Then I will have B, which is like J1, J2, Jn. So I multiply this with this and I construct here now B, which is I1, I2, In, J1, J2. So now you can see that this is going to have M plus N labels or M plus N subscripts. And this has M, this has N. So for all the 3 to the power of N plus N components constructed in this fashion. And you verify for yourself that given that this transforms like an nth rank tensor, this transforms like a, sorry, this should be easier. If this transforms like an nth rank tensor, then in that case, this transforms like an n plus nth rank tensor. So the way to do this kind of proofs is the following. Take this as the definition. So this definition must hold in any basis. So given that it holds in this basis B, with respect to basis, okay, instead of calling B, let's call this as C. Okay, so with respect to this basis, it holds. So then it should be true. Now with respect to this basis B prime, all that you need to put is B prime equal to this times A prime here and C prime. That's by definition because that's how I've defined it. Then after that, use the fact that this transforms like a tensor, this transforms like a tensor. So that will give you the relation between the prime quantities of these A's and C's with the unprimed quantities. Then from that, obtain the relation between the prime quantities of B with the unprimed quantities of B. And show that that relation is exactly like that for an M plus N rank tensor transformation. Okay. That is the way of it. Okay, so by doing the outer product, I constructed therefore from, so that suppose it was rank 1 and rank 2, I can construct a rank 3 tensor. If I have both of the rank 1, which is what we did earlier, I get the second rank tensor. So by taking the outer product, what we have done is we have constructed tensors which have higher order than the starting tensors. But we also saw that we can do this operation. Given two vectors, we also have an inner product. So I will define the inner product of two vectors in the following way. Now this is how we have defined the inner product, which now in our summation convention notes that this is nothing but Ui Vi. Okay. So I write specifically here I equal to 1, 2, 3, and this is the same as Ui Vi, because that's our summation convention, repeated indices are sum. Now given that U and V are vectors, and the inner product is defined like this, how does it transform under your rotation transformation?
It remains invariant.
It remains invariant. So what do you call this product? Yes.
Scalar.
It's a scalar or it's a tensor of rank 0. So when I took the inner product of two tensors of rank 1, I got here a tensor of rank 0. So if you look at again this, so from Ui Vj, if I construct, what will this be? If I just do Ui Vj, so I have two tensors of rank 1. If I construct this object, this is like doing this operation, right? Because now you have 9 elements. How will this transform? Ui Vj?
Like tensor of rank 2.
It will be like a tensor of rank 2. But now what you can see on the other hand, if I took simply Ui Vi, and again I want you to emphasize here, because it's repeated, it's not just one element, but it is U1 V1 plus U2 V2 plus U3 V3. This object, on the other hand, this transforms like a scalar. It's like a tensor of rank 0. And this whole quantity, if I define Vij like this, you will see that this is nothing but Ti1. So defining my Tij like this. So given two vectors ui, u and v. So if I have u and v with the components ui and vi, I could do two things with it. I could construct this object, which is a second rank tensor. And then I could construct this object, which is equal to this, but which is in terms of this. But if you look at this, what is this in terms of this second rank? So let's write this here. So if I look at the matrix form of this Tij, it's actually instructive, right? This means u1, v1, u1, v2, u1, v3. See, initially what I would suggest is that you write things explicitly, because what happens is then that fixes for you the ideas. And it's not like you're simply manipulating some expressions. After you become a little experienced and smart with using this, then it's okay if you don't use it because the ideas are fixed in your head. So the matrix form of this is this. Now P21, this will be U2 V1, then U3 V1. Then here you're going to get U2 V2, U3 V2. This is U2 V3 and U3. So given two vectors U and V with the three components like this, I could construct this matrix with the 9 elements given like this. And I found that the inner product of these two vectors is equal to this. But now if I look at this matrix Ti, this is nothing but Tii, because repeated index summation means this. But what is this Tii in terms of this matrix?
Trace of the matrix.
So this is nothing but trace of. Okay. So what you find? So what have I done? I've taken the second rank tensor and now we took the two indices to be the same. So once I have two indices to be the same, and if I don't tell you anything else, it means it's summed up. Then what I get is actually the trace. But then what you find is that your trace remains invariant under rotations. Because this is nothing but your scalar of the number. And this is something which you already know. So in other words, what it tells me is that even defining this trace of T is a tensor of rank T. Because it's a scalar. Okay. And it remains therefore invariant, it doesn't change under rotations. And if you look at now the way we have defined trace of T, it's nothing but Ti. So essentially what we did was these two indices we put to be the same, and then we summed up over the equalized indices. Okay, and that gave me a scalar quantity. And that particular operation is called a contraction. So this process where I put these two indices to be the same, and then because it's the same, I said that you have the summation. That is called as a contraction of the tensor. And what you found here is that when I contracted this tensor T, I ended up with a tensor which is of rank 0. So I contracted a second rank tensor and got a tensor of rank 0, which means that we'll see later that if I contract a mth rank tensor, I will get a tensor of rank m minus. Because two indices have gone away because of contraction and summation. Okay, I'll continue with this next time. That is at the same time. Okay, let me stop here. Wait, this. Go here and first of all, either journal. Then stop recording. Then after that, do mute it first. Isko mute karo. No, because we have to go over this. Mute that.